should be live now, and good morning, Jack. Hopefully you're there with us, and Noah also. All right, well, let's get to it. So let's see. Last time we cut off, we were talking about the stack and wanted to talk a little bit more about the stack itself, and then also the scanf function from C. So let's see, where did I put? I've got an example here. Oh, I think I didn't copy it over from my thumb drive. Okay, so let's just open up my chaco.asm file, the sort of example that we've been running with. Okay, so what I've done here is I've taken the sort of stupid program that we've used as an example that basically just takes two numbers as input, and I think it computes the square of the sum and the square of the difference, and then multiplies those two things together. Okay, so whatever. It's not doing anything particularly fancy, but I've written it so that it also uses scanf now to take input from the user rather than me having to hard code the values that I want. Okay, so what information do you have to pass to printf to print something? Okay, to print a string. Hmm? Okay, you need to, well, you put things into a register, but what do you have to have a string to print, right? So what information do you have to pass at bare minimum? Huh? Nope. It goes in X0. It has to go in X0. It's going to be a memory address, right? So that string is sitting somewhere in memory. You got to pass a pointer to it that says, okay, here, printf, here's the string that I want you to deal with. Okay, so that goes in X0. Um, depending on, okay, that was weird. Depending on what you're printing, you also would need to pass like numbers, right? So if you print a string that has a number in it, like it's got text and then the place where printf will plop in a number, then those subsequent things go in registers X1 up through X7. All right, what happens if you want to print more than 7 things plus the string? You kind of run out of registers. So then you have to go to the stack. Yeah, okay. But at minimum, printf needs a string, right? That's the whole point of it. Well, where is that string located? You've got to tell it. It's not psychic. Okay. So at the very beginning, I've got two strings that I've made that I just called please1 and please2, which are going to be the things that prompt the user for input, right? So what I'll do is I'll print please1 and then immediately go into the routine to scan and get input from the user, and then ditto for the other one. Okay, but in particular, um, I need to, so the first command there, right, is I'm just taking my link register and my stack pointer and um, putting them onto the stack so that I can preserve them, right? That's the standard start to a program. And then the second instruction there, load register x0 with, okay, if you put an equals in front of the name of an object, in this case a string, what does that do? The equals. Or what do you think it does? Bueller. Well, what do we have to pass to printf? Right, okay. So what is the memory address of please one? Do I know? No, I don't, but I can reference it by putting the equal please one, right? And so that just, when the assembler goes through this, it says, okay, whatever the address of that is, I'll plop it into um, that spot. Okay, does that make sense? Yeah. Okay, um, so all I've got to do in this case, because I'm only printing text and I'm not going to also print a numbers or output, uh, is to just print, or sorry, just pass the memory location of the string. For the first one, it's please one, and for the second one, same idea, but it's please two. Okay, um, and that will, and then I branch and link to printf, and it spits out the appropriate data. Okay. Um, all right. So here's one question. Why is it that in please one and please two, I did not put a backslash in at the end of those strings? I could have. It's not wrong to do it, but why did I choose not to in this case? Well, what does backslash in do? New line, okay? Why would it maybe be a good idea to not have done a new line at the end of each of those strings? On that same line, right? Um, yeah, so that's why I did it that way. This is also why there's a space in there between the colon and the quote, so that when they start typing a number, the user starts typing a number, there's a space between the colon and when they start typing. Okay, that's logical. Okay, so great. So that's the printf stuff. Now, scanf is how, like printf, uh, we need to pass it some information. And, you know, the one in my office is doing that too. I don't know what the deal is, where it just blanks out for something. Oh, look, it's a spammer. Yay. Um, report them for spam. I think this is a bot account. And I'm going to block them. Yay. And then delete their message. Okay, yay, my first ban. Um, okay, so what was I saying before I was so rudely interrupted by the spam bot? Um, right, okay, what do I need to pass to scanf? Well, I only need to actually pass one thing to scanf, okay? And that's basically a format string that tells it what kind of data it's to be expecting. Okay, and furthermore, I can only give it one thing, right? Because if I type like two numbers with a space in between or something, right, it's not going to know that I'm typing in multiple things, okay? Um, so what kind of number do I want to um, uh, to be inputting for this program? I want an integer, okay? And what format is the user going to be typing it in? Well, it is ASCII that they'll be typing it in. So let me rephrase what I mean. They're not going to be typing it in hexadecimal, are they? Okay. So I could accept input from the user in hexadecimal, but in this case, I probably want to accept it in decimal. Okay. Um, and I'm right. Okay. So hence the format string for what kind of data I'm expecting is an integer, a long, okay, so 64-bit thing. And um, I'm going to take that as in decimal format, okay, not, um, yeah, not in hex or binary or something. But like with the format strings for output, you can also do all of that stuff for input. So if you wanted to have a program where the user gives you something in binary, like you can totally do that, okay, or hex or whatever. But for the sake of this example, I just had it be in decimal, and that's that. Um, okay, so uh, I just need to pass that information to scanf. Well, it's a string, so like with printf, I'm not going to pass the string itself, but rather where it's located in memory, okay, because it won't fit in a register by itself. And so what am I going to do? I'm going to put in register 0 whatever the memory address of the scan string is. Okay, just like with printf, only this time it's gonna, that's really annoying. And it didn't do this on Thursday, so um, this is the trouble with beta software, right? Anyway, okay. So, and then once we've got that string, or sorry, the memory address loaded in, then we can branch and link to um, scanf, and that's that. Okay, now, where is scanf going to return whatever the user has typed? Well, it can't necessarily stick it into a register. Theoretically, in this example, it could, because we're just prompting for a number, and a number will fit into a 64-bit register, okay? But what happens if you're using scanf to do something like ask the user to type their name? Well, then they're going to be inputting an ASCII string, and that ASCII string may or may not fit into a register. Probably it's not going to fit. Okay, so if it won't fit into a register, where do you have to put it? In memory. And where in memory do we have as sort of our workspace? The stack. Okay, so it's going to put things on the stack, and then um, when we want to then retrieve that stuff, we have to then know where is it on the stack that it's going to be stuck at, and then go and get the appropriate cell out of memory to do something with it. Okay, or if it were a string, you'd want to know, okay, where does the string start? How do you know where the string ends? Huh? Yeah, you look for the null terminator at the end. Okay. Okay. All right. So the rest of this program is basically the same thing. Okay. I'm just going to print, please input a second number, pull the second number. Okay. And then the other thing that I'm going to do is I need to know where to pull the two numbers from once they're put on the stack, okay? And so, let's see, hang on one second. Yes, okay. So when Scanf runs, okay, it's going to put a number. It's going to expand the stack, however much is necessary, and then also put the input starting at the new stack pointer, okay, whatever that is. Okay, so where is the input number? It's sitting at wherever the stack pointer is, okay, once scanf finishes. What's the next instruction that I do? Okay, so this add SP minus 16. I'm going to make the stack bigger, okay? And the reason I did that is basically, well, I don't think actually technically I needed to, but went ahead and did it anyway. Basically, I'm making room for the second number to come in, okay? And let's see, why did I do that? I'm not sure why I have this instruction right here because it doesn't, it's going to get overwritten, but, I'm sorry. Forgot one thing. You have to pass two things to scanf, not one. You need to tell it where the current stack pointer is. Okay. And so where do I have to put that? In X1. Okay. So sorry, you have to pass two pieces of information. And you might say, wait a minute, why do I have to pass it the stack pointer? Couldn't it just go to X29 and get it itself? So this is sort of the thing about subroutines, particularly when they're external ones like printf and whatnot, they get their own stack, right? So its stack pointer might be totally different than what ours is. Okay, so sorry, so I have to pass it also the stack pointer so it knows where to stick stuff. Okay, yeah. All right, so then I'm going to expand the stack. That's that middle instruction, the add SP minus 16. And so I added minus 16. Why did I add a negative there instead of a positive? Yeah, because the stack grows downwards, so it goes from high memory address to low memory address. So to expand the stack means that your stack pointer goes down in memory, not up. Sorry. Okay. So SPJACK stands for stack pointer. And it just tells us basically where the top or bottom, depending on your perspective, is, where the stack, its limit is. Okay. All right. So then the second part here, this chunk right there is basically the exact same thing as before, right? I'm gonna print a prompt to the user to say, hey, type me another number, and then set up scanf to wait for that other number, and then we're Gucci, okay? All right, so that part, like I said, works the same as basically I just copied and pasted from the previous part and then, changed please 1 to please 2. That's all I did, okay? All right, then the next, the salient stuff is this part right here, okay? Let me put a space there. Which is I've just prompted the user, okay, for input. And scanf puts those things on the stack. Well, if I want to go and retrieve them from the stack, then I need to load them back into registers to then do something, okay? So the first instruction here, okay, this format looks a little different than we've had before, which is it's going to load register X1 with what? Okay, what do you think the SP thing there means?
Like what's on top of this stack.
Yeah, okay. So if it were SP with no brackets around it, it would mean the actual value of the stack pointer from the register, right? Okay. When you put brackets around it, what it means is not to load X1 with the stack pointer, but to load whatever's at the stack pointer. Okay, so this is an indirect load, right? You're saying, okay, take the stack pointer, treat that as a memory address, go to that memory address to pull data rather than pulling it straight from the stack pointer register. Okay, does that make sense? Sure.
So stack like equal or we can move into like a pop out.
What do you mean a pop out?
So I mean like so once you like a pop out so you have like a stack, right?
Mm-hmm.
Once you pop out something, then that they will be just removed, right?
Well, okay, but it's not removed. I'm just taking the thing that's
Okay.
there and copying its data into a
Just
register.
copy.
Right. So it's not really a pop in the sense that I mean, I guess you could think of it as a pop, but so in those of you who did 211, did you guys talk about stacks as sort of an abstract data object?
Yeah.
And then you talked about pushing and popping,
Yeah.
right? So um, to an extent, our stack is we kind of are pushing and popping in the sense that we're putting more data on and then possibly taking more data off, but we're not. It's not truly popping because if I read data from memory, all I'm doing is reading data from memory. The data is still there in memory. The pushing and the popping is when I also move my stack pointer,
Mm-hmm.
right? But I'm not doing that here, or at least not in this instruction, right? I'm using the stack pointer, but I'm not changing its value, okay? Um, so I can leave things on the stack for future use. I don't have to push and pop every time, okay? Um, yeah, so I guess that's one degree to which this is a little different than stacks from data structures. Um, okay, so if that means to take something from the stack pointers, um, basically from the bottom of the stack, what do you think this instruction is going to do? It's going to load x0, load something into x0 instead. Okay, fine, but sp comma 16. What do you think that's going to do? Yeah, it's relative to the stack pointer. Okay, so this is, I'm doing indirect register loading, okay, and I have an offset. Okay, so in this case, the offset is 16 bytes. Okay, so the 16 is in bytes. Um, all right, and so what that will do is it'll pull whatever. So let's say that the stack pointer is at memory location 10, then the second instruction would be pulling from memory location 26, right? 16 bytes up. Okay, does that make sense? Yeah. Um, okay. And then um, the rest of the program, all of this stuff down, was basically just everything I did before. Okay, but I do have to be a little bit careful because your stack should basically, how big is your stack when the program starts at the very beginning? It's nothing. You haven't put anything on it. You put stuff on the stack. At the end of the program, you need to pull it off the stack. You grow the stack pointer at the beginning of the program, you better shrink it to compensate at the end. Okay, which that's more like pushing and popping. Okay, so every time I do an instruction that expands the stack, I need to have a mirror image instruction that's going to shrink it. Okay, so at the very beginning of the program, right, I store 2 registers, and this will grow the stack. Well, at the end of the program, I need to shrink the stack and pull those things back out of memory. Okay, here I grew the stack, and so here I have to correspondingly shrink the stack. Okay, so that my stack stays, or basically starts and ends at 0 size. And if you don't, then something funky will happen when your program terminates. Okay. All right. So let's run this thing and see what's happening. Okay. So let me save that, and let's go into. All right. So first off, let's just run it. Oh, right. Okay. Sorry, this sometimes happens. Um, Depending on what format your memory stick is, sometimes things that are executable, when you copy them to a memory stick, they don't come back as executable with executable permissions. Um, so let's just reassemble everything. All right, so I want to do, what was it, Chaco, and then okay, and now I've got an executable. Okay, so great. Nothing particularly fancy. Okay, but now what do we really want to do? Let's throw this thing into the GNU debugger and actually look at the stack as we're executing through the program. Okay. All right, so I need to reassemble it with the debugging stuff. All right, so let's do. Okay, so the static thing is essentially what's going to happen there. So I'm using printf and scanf, right, which are programs basically that are live somewhere else. Dynamic linking is where I don't have to like include all of those in my executable. I can just say go to them, and the operating system will link me to the appropriate place. If I statically link, it essentially copies the program printf and scanf into my program. So you get a much bigger executable file, but it will mean that when we do the stepping, we won't croak when we hit the printf or scanf lines. And yeah, so for the sake of demonstration, I'll do that. But in practice, you don't want to use static linking because it makes your executables bigger, right? Okay, so cool there. All right, so now we want to do, oops. All right, so GNU debugger, and I want to break main, and then I need to run, okay? And like before, we can look at the registers, or we can look at the stack. Do we really care what's going on with the registers right this instant? No. We know that memory addresses are going to get passed to them because of and that their numbers are going to get stuck there. Okay, but the registers are old news, right? So let's concentrate on the stack. And so if I want to look at what's in the stack, then I need to use X for examine. Um, and where do I want to start? Well, I'll start with wherever the stack pointer is. So this will show me 16, well, I guess what it would be 16 quad words starting at the stack pointer going up. Okay, so if I run that, then where is, well, actually, I do want to look at the registers. What's my stack pointer? Right when the program begins. It's blah, 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 090. Okay, fine. So, hence, what's at the top there? 090. Okay, and then everything that's above that is, some of this is not in the stack. I'm printing too much, but that's okay, right? So, because we have, our program really hasn't done anything yet. All right, so let's start stepping. Okay, so it just ran the instruction store pair, and now look what's on our stack. Well, first off, what's the stack pointer now? Blah, 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 080. Okay, and that's because the store pair command, right, is going to take two registers, shove them onto the stack, and it deducts, or well, grows the stack by 16 bytes right before it does it, so that there's room to put the things. Okay, that would be equivalent of doing a, you know, an operation where you subtract 16 from the stack pointer, then you put one on, then you put the other on, but you get it all in one instruction, which is kind of nice. Um, okay, and so what do we have on our stack now? Well, at the stack pointer, what do we got? We got 7F blah 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 090, which was the previous value of the stack pointer, right? And what else do we have? The 000 40000944, which was what? It was the previous value of register X30 that we were saving um, for later. Okay. All right. So we're good with that. Yeah. Questions? Preguntas, Fragens? You guys online? How are we doing? Um, all right. So let's just keep stepping through this stuff. All right. So I'm going to branch to printf. Okay. I just came back from printf. And now I'm setting myself up for the scanf part. Okay, and now it prompts me for the input. Okay, so let me just put in, say, 5. All right, and now let's look at the stack. Oh, that's interesting. I think I should have grown the stack by another 16 bytes before I did that. Okay, so why am I concerned? Yeah, I overwrote my old value of the stack pointer, right? So I may have a problem when this program, when we get to the end. Okay, why did that happen? Uh, no, I actually haven't yet because line 19 hasn't executed. That would be what's about to execute. So what I should have done was I should have added 16 bytes to the stack before I branched to scanf. Okay, because what is scanf going to do? It's going to take its data, whatever it gets as input, and it's going to start to put that on the stack. Well, I passed it the stack pointer and I didn't grow the stack. Okay, so what was sitting here in memory at cells 080 and 087? Okay, the old value of the stack pointer. But I just handed that exact stack pointer to scanf and it said, okay, I'm going to put my data there. Great, bro, thanks. And so what happened? It overwrote something. Okay, that's not good. All right. So we may have an issue when we get to the end of the program. So let's just see what happens. Okay, but does it make sense what the issue is? Yeah. Okay. Now the next instruction I actually didn't mess this up, which is to grow the stack. And now what's my stack look like? Okay, it starts at 070, and I still have the stuff that was at 080. I haven't changed any of that. I've just changed where the stack starts. And in this case, what is in the memory cell 070, oh 07, what's in this row? Like the 430 and then the 02, does that mean anything? No, that's just garbage. Okay, it's not useful to us, but that's whatever happened to be in memory before we got there. So okay, we can nuke it, uh, and in this case, I'm just gonna printf and then scanf. All right, so let's do that. So step, 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 step. Okay, and let's say 6. Okay, so now look at what I've got. What's in the memory address where the stack pointer is? 6. And what's 16 bytes further down? 5. Okay, those are the two numbers. Okay, so I've got 6. Okay, and let's be clear, really, where is 6? It's all of this, right? Because what size did I associate with this stuff? 32 or 64 bits? 64, and so that takes up 2 of these chunks. Okay, does that make sense? Um, yeah. All right. So have I been very efficient here? No, not really, because I've kind of wasted. Like I'm not actually using this little piece of memory. I could be, but I'm not. Um, okay. So on the subject of the stack, and I know we talked about this at one point. When you grow the stack or shrink it equivalently, what kind of it's like I always grew this thing by 16. I could have done 32 or whatever, but why did 16? There was something special about 16. You guys remember? Well, there's that, right? Okay, it changes the second hex character by 1. Okay, so in particular, the stack pointer stays, well, the stack pointer always ends in a 0. Okay, another way to say this is that the stack must be 16 byte aligned. Okay, so your stack pointer's final digit must be, or final hex digit must be a 0. And that's a hardware thing. Okay, so that's just how the memory circuitry or whatever in the ARM architecture works for the stack. Why did they do that? Not entirely sure, but thou shalt 16 byte align your stack. Um, now, this, by the way, I ran into that lesson or learning that lesson the hard way last year. Okay, so last year, uh, like this year, I have a copy of Linux running on my laptop and some emulation software that allows me to write and compile and execute code that's in ARM architecture, even though my laptop's an Intel architecture. Okay. Okay, fantastic. So I wrote a program and I'm like, well, I only need 8 bytes, so I'll just grow the stack by 8 bytes. No big deal, right? That way I'm using exactly what I need. And I ran it on the emulator. Worked fine, no problem. I took the exact same code, copied it over to a Raspberry Pi, and executed, and what happened? Error, right? Bus error. And it was because does the emulator care how the stack is aligned? No, it's just numbers to it. Who cares? There's no circuitry. But the actual Res Pis do because that's native hardware. Okay, so anyway, all right. So now that I've got my two numbers, 6 and 5, they're sitting in the on the stack someplace. And if I want to do something with them, I better pull them off the stack, or rather load them from the stack. That's maybe a better way of saying it, and then start doing things. Okay, so so I'm going to pull the. Let me step one more time. Okay, so those two instructions, I've just pulled the two numbers from the stack and put them into registers, 5 and 6. Or sorry, 0 and 1, but the numbers were 5 and 6. Right, so I can load data off the stack, and they're sitting in the registers 0 and 1, and then the rest of the program is basically the same as it was before. It's going to do some arithmetic with these things and then spit out a number. Okay, big deal. Okay, so let's continue. Um, Actually, what I can do is this. Okay, continue will just say basically stop the stepping and just keep running all the way until the end. Okay, so inferior process 1 exited normally. How do I know that it exited normally? What's the signal for exiting normally? What was in X0 when I quit? That's where the operating system expects the exit status code, and I put 0 there at the very, very end. Okay, that signals exiting normally. I'm actually a little surprised that this did exit normally because of the issue with the stack pointer. Yeah, so I'm a little surprised that worked correctly. Um, Basically, what I'm suggesting is if we go back up to our code, what I should have done right, I should have um, I should have grown the stack and then correspondingly shrunk the stack. Okay, so let's recompile and run this. Okay, that's better because look what is sitting at 080 this time, right? I did so I didn't nuke the number. Uh, yeah. Okay, good. Now this, by the way, means that if you're taking in, um, this is where I think we'd have to be a little bit careful. What about if you're taking in a string as input? Yeah, you got to make sure you got enough stack, which partly means you need to know how long the string's going to be so that you allocate the correct amount of memory. Um, and I'm not sure if there's a way to limit basically how long the input is. Um, I'll have to do a little bit more research on exactly some of the innards of Scanf. But do you guys see the problem? Like, what happens if you type like an entire novel of Shakespeare, right, and you only give it 16 bytes worth of stack to put the data in? You're going to have a bit of a problem, right? Um, so yeah, actually, I'm not sure how we would deal with that. Um, I'll have to think. So okay, anyway, um, okay, so are we kind of is the stack making a little bit more sense?
Yeah, I have a question.
Sure.
Can you like expand stack kind of dynamically? Like depending on the input size, you can expand your stack
Uh,
in any way.
that would be the solution of the problem, right?
Yeah,
Is if there were a way to dynamically expand or shrink the stack,
yeah.
and I'm not sure.
Okay.
Um, that would make sense. Like if if there were basically a way to tell scanf like, hey, here's the stack pointer currently. Expand the stack however much you need to put the data on, and then just give it to me. Rather than putting it exactly where the stack pointer is, where you have to know in advance how much data is coming in. I'm not actually sure about that. Okay. And it may be the case, and this is something I'll have to look at. It may be the case that if I'm telling scanf to pull that the user is going to input a number, that it just puts it on the stack. But if I tell it that the user is going to input a string, it knows that's exactly going to be the problem, and it does something else instead. And I'm not sure. Does that make
Yeah,
sense?
it makes sense. Yeah.
Yeah. So uh, I'll uh, I'll do some research into that and see if I can figure out that answer. Um, huh? Well, we can. But I don't remember the exact format string for if you're telling it that the user is going to input a string. I mean, we can find out real quick. So, I mean, if only we had the bastion of all knowledge of Western civilization at our fingertips. All right, so it's S for string. Okay, that's maybe not shocking. Um, and it looks like there's some stuff for expected size. Um, yeah. So let's just change the format string to S for string. Okay. Now the program is going to be garbage in terms of the arithmetic because it's just going to be pulling the ASCII or it's going to be pulling numbers and treating them as their numbers, not as letters. So the output of this program we don't really care about. But so let me quit here. and then let's GCC or assemble it. All right, so break main, run, step, oops. All right, so now let's look at what's on the stack, okay? Okay, so what's on the stack there? Well, that doesn't seem like it's quite what I would have expected it to be. Well, okay. So what can we almost certainly guess is going on here? Well, anybody have an ASCII table handy? Right. So 687361266157. Okay. Well, 61 and 61 are probably what? A and B, right? And then um, 62 would be, so we got A, B, A, but then why is that 57? Because that should be a capital S. Um, oh, it's the order. Sorry. What's five? So let's pull up an ASCII table and not be idiots here. All right, so what is capital W? 57. Okay. So there's capital W, A, B, A, 73, S, H. Okay. So where's the rest of it? Well, we typed a space. All right, so let's rerun this. Oops. Damn it. All right, so now look what we've got. Well, we've got the same stuff as before, right? W, A, B, A, S, H, capital A, L, right? Sorry, I was looking at the C and cognitive dissonance, right? And then continue, okay? All right, so let's just count it up here, right? WABA, SH, okay, so Wabash, all ALWYSFIGHT null terminator, and I have no idea why it put FF there. Okay. Um, was it? Oh, yes, yes. Okay, no, that's exactly what happened. And that makes sense because how is it going to be outputting if you're doing things one byte at a time, then um, uh, you're going to be outputting it one byte at a time. Okay, so what happened here, right? So the 7.4, right? And this is the problem with Indian is what address is 7.4 in? Oh wait, oh, 1, 2, 3, right? So it's actually sort of reverse it in your mind, right? Because of the order issue. Okay. And so if I'm going one byte at a time and I hit my null terminator and I'm done, well, then I never actually touched memory address blah blah 083, which would be where the FF is sitting. Or I'm sorry. Yeah, no, that's right. Because the this chunk is 0 through 3, 4, 5, 6, and 7, uh, 8, 9, A and B, C, D, E, and F, right? Because it's 16 bytes. Okay, does that make sense? Yeah? Okay, so we've got an issue there, right? Because we've just overwritten some of the stuff on our stack. That's a problem, right? Um, it also begs the question then, how do you deal with, so what happened when I typed this with the space? Yeah, it didn't take it, right? Or rather, it just stopped when it hit a space. Um, and no, because the space character is not actually 0, 0, right? I mean, if it were, that would be an obvious answer. Is it hits 0, 0, and it's like, okay, I'm done. That's the null terminator. But the space character is actually not, right? The space is, where is it? Yeah, here. It's hexadecimal 20, not 0, 0. Okay. Um, yeah, I mean, part of that just okay, I guess whoever Scanf just expects when you hit a space to know that you stop. Great. Um, okay, I'll say la vie, right? Um, okay. So yeah, let me do some more digging on exactly how we address some of these issues. I mean, do we agree that we see and understand what the issues are, right? How we solve them is another matter. Okay, we good? All right. So I wanted to return briefly um, uh, to this business about subroutines, okay? Because and Will asked this question I think last time, which was, how do you do, like, why is it there's no branch conditional and link, right? Um, and I guess part of the reason would be, like, let's say that you were to start. Let me just make a blank file here. Let's say you wanted to do something like this. Okay, so let's say that you were to write something in C or Java that's basically this kind of construct, right? So for example, I could say, um, let me just say, um, like that. Say some number is equal to 0. Okay. Um, what would this sort of look like if you were to write it in assembly? Well, you could do something like, um, well, let's see. In this case, if I'm testing whether or not something's 0, let's suppose that num, that we've got the number, whatever it is, sitting in x0. Okay, we might have to move it there, but let's say it's already there. Okay, then what could I do? I could do compare branch non-zero or compare branch 0 um, to stuff, and then um, I could do, say, for example, stuff, do stuff, um, and then if I have, say, other stuff, so if I did something like this, oops, something like that. This maybe looks a little bit complicated, but essentially what's the idea here? That when I hit compare branch 0 and I jump to stuff, all right, where stuff, when stuff finishes, what's going to happen? It's just going to skip down here and keep going, okay? And I don't need to keep track of the link register there because do I need to go back to where I came from? Not in this case, okay? And so you can have labels that are in part, like a label doesn't have to be just for a subroutine. It can be like a little piece of a an actual routine. Does that make sense? So they can be inside main or another routine. And doesn't that look a whole lot like the if then else construction? Yeah, kind of. Okay. So you can do stuff like that. I mean, one thing we could do, right, is uh, why don't we actually just let me make one more new file here. Let's take this and something like that. And then let me just save this as, um, well, let's make a new folder here. Huh? Oh, yeah, yeah, of course. Um, um, Okay. But if we look at, okay, so if we look at then what the assembly that GCC produces, right? Okay, what do we got at the top? Well, of course, we've got to define our strings. Okay, so then no shock there. What else do we have? Okay, some junk, some junk. Here, okay, it's interesting that it did it as two separate instructions rather than using compare branch zero or non-zero. Okay, whatever. So what has it done here? It's um, compared, then branched on non-equal to the else case, and I suppose this actually makes sense. Um, so if it branches to the else case, then that means it does the else but not the if, right? Or the then, right? Okay, so what's going to happen right here? What is this going to do? It's going to um, uh, this business right here. Oops. Blast. Okay, that's going to be the printing the else case, right? Which in this case was right. Print say the number isn't zero. Now, interestingly, here, even though I wrote in my code printf, what is it branching to here? What is it using to print? Puts. What is puts? I have no idea. Have we seen that before? I think the last time I compiled something, we didn't see that. So that's interesting. Okay. Uh, and then, so the then case is here in location L2, right? This would be printing the number is zero, right? But okay, so what's going to happen if let's say that I typed in or that the number was 5, okay? So I would hit compare number and 0 and 5 and 0 aren't the same, okay? So I would jump to L2, which is here. So I would do this bit and then after I return from puts, where am I going to go next? Well, the next line. Does that make sense? Okay. So I don't have to have a branch here that says to go to L3. It's just going to go to the next line. Okay. However, what about why do I have to have the branch there? Yeah, because the next line is something I don't necessarily want to execute, right? Okay, so does this make sense what I'm trying to say about how you can have labels sort of inside um, points in your routine? Yeah. Um, or they can be like genuine subroutines. Okay. But for subroutines where you need to go back to where you came from, that's where you need to branch and link. Here, we never needed to branch and link because it was all in line. Okay. Well, with the exception of whatever put s is or puts. Okay. Um, okay. Does that kind of make sense that you can put labels interiorly? Okay. All right. So there's one. Just one last little thing before we quit, and we'll continue talking about this next time. Um, so let's just remind ourselves, what's the difference between W0 and X0? Yeah, W0 is the lower 32-bit chunk within X0. Okay, so there is a command to either read or write an individual byte of memory, okay, where you would not shockingly need to specify what address of memory you're going to pull something out of. Okay, so if we think about like what our string example from a minute ago, if I wanted to have the user input a string and then I wanted to read that string, say for example, well here's a good example. Um, did you guys do this in when you were in 111, where you had a number like let's say 37, the actual number 37 as an int, and you wanted to produce a string that had the symbol 37. Okay, or you could go the other way, which is let's say you've got a string that has like a negative symbol, then the 3, then the 7. Could you read through that string and produce the number negative 37? Okay, so this is basically int to string or string to int, depending on which direction you're going. Well, guess what we're going to have as an assignment at some point? You guys can't see my evil smile because of the stupid mask. Okay, but that, right? Well, if you're going to do that, then you have to be able to read one byte at a time. Okay, this part is really silly. If you load a single byte from memory, what do you guys think? Would it matter if you put it in W0 or X0? Why would it, right? Because if it's a single byte, you're only loading in, 8 bits worth of stuff, and the fact that you have 64 bits to work with is kind of, well, whatever, right? You can only put bytes in W's, not X's. Okay. Now, Matt Clark last year thought this was really silly. He's like, okay, so what you're telling me is it'll fit in either a medium box or a large box, but I have to put it in the medium box, even though it fits in the large box. Yes. Okay. So maybe actually think of it this way, right? How many of you guys have gotten a package from Amazon where like you order something that's like, say, the size of this stupid little pocket calculator, and it comes in a box that's like this big, and you're like, Amazon, that was really silly. Yeah, maybe it's kind of like that. So anyway, all right. Well, this was fun. I will see you guys on Thursday.